Today, in this next 30 minutes, I'd like to talk about high performance cutting on drilling operation. We know high performance cutting for milling, for turning, but now we want to implement high performance cutting also in drilling operations. So first of all, what is a drill? It's very similar to this component what you can see here. You have a certain tool diameter, you have a certain tool length, and when you look to a drill, it looks very similar. And the challenge here will be the tool overhang and deflection. It's not a guided tool. We have just two inserts on the front, and there are some forces acting on such a drill. A force acting on here on the front. This force, it first will be the self-weight of the tool. If the tool becomes heavy, this is also hanging down. Yeah, chip location, cutting forces, feed forces, and so on are acting here on the drill. Basically, this is not a critical situation if the tool is deflecting to the side, but there are size variations, there are directly influence to the surface finish, and sometimes the whole drilling process will not be stable anymore. So what is the calculation for this deflection? You can see here the small f, which is the deflection. And in my formula, you see that the capital F will be the cutting forces acting radially in L cube. So the L, the tool overhang, in this deflection calculation will be in cube. It's not just 100 millimeter tool overhang, it's 100 into 100 into 100. When you look below the line, you can see this I. This I will be the bending factor of the material. And here it's P into D times 4 divided by 64. So also the tool diameter here is very, very important. So keep the connection of the tool as rigid as possible. This is what I like to show here, what will be the message. Yeah, mounting angles of inserts is very important. So here, the nominal force which is acting under 90 degrees on each cutting edge, this will be an example of a drill with a W-type insert. When you look to the forces acting inwards and acting outwards, then you can see that there is a slightly force acting outwards. And this is exactly the principle how we are building the drills. It should deflect a little bit to the outer direction, that when the tool retracts, he can retract without any contact to the bore surface, and it will not destroy the surface. So this principle, it seems to be neutral. It seems to be perfect on size, but this is not the way how we are building the drills. The last example, you see a dramatically high force acting inwards, and this force acting inwards means that we are drilling undersize, and when you retract the tool, we will create a dramatically spiral fluid. When you look now to, can we connect the sound, please? So you have to hear the sound here. I like to show you the newest generation. This drill is called a Pentron. This Pentron, you can find this 5 including in this name. Hope it will work now. Let's go back again. We start here in a tool steel with about 1100 Newton tensile strength with a linear feed rate of 0.18 per revolution and about 200 meters or 220 meters cutting speed. These are the parameters what you can find in the catalog. But we in our test field, we have to check what will be the maximum feed rate, what the tool can do. So 0.18 is standard today. Now we increase the feed to 0.22. And interest will be on the end when we are measuring all the different sizes by all the increasing feeds per revolution. Normally a drill with index insert is drifting away to the outer side. But here we are creating holes in a tolerance field of 20 microns. if you hear 20 microns, it sounds like H7 class, but it's not H7 class. When we change the inserts, we have manufacturing tolerances. Now we are running the tool with 0.26. The last hole will be with 0.3 per revolution. And this is a single point cutting tool. No reduction while entering. And the noise shows that chip evacuation is easy. And chip evacuation is a basic challenge for all such kind of drills. See, here will be the deflection. When we increase the feed rates, the tool diameter will be always the same, more or less. What will be another challenge in drilling with indexable insert drills? This is definitely interrupted cuts. Interrupted cuts destroys all what we do when we are balancing the cutting forces, when we try to achieve a cylindrical hole. An interrupted cut means that the tool is cutting only with the inner or with the outer insert. So we need a lot of rigidity, but look to a 5D drill doing interrupted cut, just drilling a half hole, a half pipe bore. Even this, such a tool have to do. Here we have to reduce the feed rate to roughly 50% of the nominal feed rate. Another option, entering in a component on an angle. Normally you have to do a face milling first here to enter straight, to have both inserts in touch even when you are entering the bore. But just reducing the feed to 50%, so something in between 50 microns and 100 microns, or 0.05 to 0.1 millimeter feed per revolution. This tool is not dry cutting, it's minimum quantity lubrication, MQL, just for doing the videos. Otherwise, a lot of water will going around the tool and you will not see anything. Yeah, another version, enter a component just on a corner. Just reduce, not the cutting speed, only the feed rate, and you will see it works perfect. And you will ask me, is this our daily business? It's the daily business. It's definitely the daily business. We have many applications for such a tool, and I don't know why, but people are using this tool in 5D version for interrupted cut. It's more acting like a milling cutter. As far as this tool is in the solid, just increase the feed rate to get also a good control swath, because this will be the next challenge. Long chipping materials like low construction steel, the boiler plates, and things like this. It's a soft material and cutting forces are very low, but this will be the result. And this is never ever acceptable on a drill. It could, in the best case, it could damage the drill. Yeah, it blocks the chip evacuation area and the swath will not come out. But it's dramatically dangerous as well. On an open machine, can you imagine a drill and a swath which is going around a diameter half a meter or more? It will not just cut a little bit your finger. It will cut off your ear or the nose, and we shouldn't accept this. So chip control is a basic challenge. So what happens in the drill? When you look to such a drill, we see the clearance around the tool, we see the swath inside and outside, and the noise will be, you have heard it already, it will be like this. It's a torsion vibration coming up. But when we found this situation, that the chip spirals and the chip fluids are filled out with a swath, then the noise will change from this sound into this sound. Sorry. Yeah, and yeah, but what's going on in the tool? The chip is pressing the tool body to the side. We are losing our position, our center position. So the inner insert is normally 0.1, 0.2 millimeter below the center line. And immediately we'll get a breakage here in the center. Another point, yeah, the tool is start rubbing in the bore surface and it's creating a lot of heat. And this heat and this energy will be so much that the tool is now start welding in the bore. So what will be the end? the tool is blocked in the bore, it's welded, you can't get it out, so you have to take a milling cutter to get it out. Or you have to change your drawing of the component and sell it along with the component. Yeah, this is not very often, but could be a solution as well. Yeah. Where's the chip space? The chip space in the drill, it's here. And we and other companies doing such kind of tools, we take a lot of care to make this surface in the best quality what we can get and what we can do. We have two corners or two faces, one rescinding edges and one pushing edge. The pushing edge is driving the swarf along with the rotation of the tool. So, and this is the chip area, the chip space here. But the most important surface for chip evacuation is definitely the bore, what you are producing, and the surface, what you are producing. And from a 3D hole, a 3D deep hole, if you have a bad surface finish, you will never get the swarf out easily. Yeah? The swarf will not move on this rough surface. It's moving easily on a good and a good surface finish. What will be the next challenge? Abrasive materials. Yeah, we have here stainless steel, exotic materials, nickel-based like Inconel, Hastelloy, Armalloy, and all this. And this new material, vermicular graphic iron, it's the new material where we build today the common rail diesel technology out of it. And when I remember 25 years back, my first company car was an old Mercedes, 2.5 liter, 2.4 liter, 65 horsepower. And today from 2.5 liter, how much horsepower we get easily out of it? 200 horsepower and more. So this is the new material, vermicular graphic iron, where these motors and engines are built out of it. See here, it's recorded by a high-speed camera. The chip forming is always an issue, and chip evacuation is the other issue. See, 1/3 of the cut is machined by the inner insert, and 2/3 of the cut is normally machined by the outer insert. And another point to have a success operation is choosing the correct parameters. Feed and speed is very important. So we have a 3-step principle. The first step for long chipping material, the soft material, it's very easy. Go with high cutting speed, go with low feed rate. Good material, good to machine material. This is material what you can find on demonstration machines here on the exhibition. It's always short chipping. Yeah, here we go with medium to high cutting speed and medium to high feed rate. Very impressive. And hard material which is more than 1200, 1300 Newton tensile strength, medium to low cutting speed and medium to low feed rate. This is exactly the principle where you can find in all the catalogs the parameter lists and tables. And all this together is need to design a tool which is called high performance cutting, including there are some engineers and specialists doing some models, a geometry model, a force model, FEM, finite Elemente model to optimize the tool body, the tool form, the chip fluids form, with the target to increase the rigidity of the tool body, to change bending forces into torsion forces. And all this have to be done also on the theoretical side. Now we go to some practice and some applications. You can see a traverse from such a steel 52. It's a construction steel. Yeah, we have to enter here in this area, but on the end of the hole, we exit in an interrupted cut. Diameter is 25.6. It's a core hole for an M30 thread. So the tool which was in use was a HSS tool, 13 meters cutting speed, and a feed rate of 20 millimeter per minute. See here the exit, somewhere in a welded section where the tool comes out. It's only a half hole. It's only a dramatical interrupted cut. So the cutting parameters here are 200 meters cutting speed, 0.09 feet per revolution. So at least it's 260 millimeter. With 20 millimeter here, it's roughly 10 times faster than the tool which was in use before. The HPC effect here, safe drilling with high increased cutting parameters and even under critical conditions. This is exactly what we do. We do the hole 10 times faster and with the same process stability. If you change parameters or if you change a tool, it should not go to the cost of the process stability. Yeah? And the operator should sweat all the time when the tool is running. It should be safe and uncritical. Look at this task. It's a valve block. And what you can do here is you can machine it with a milling cutter first. The entering section, here it will be very critical because we have 2 holes in a V-type. And it's a mangan steel. Diameter was 28. The tool length was 101 millimeter, the boring depth 101 millimeter. But because we have to enter under this angle of how much degree? 28 degrees. So we need a longer tool to cover the whole length of the bore. This Pentron dia 28, 5 times D, 260 meters, 0.05 for the interrupted cut when entering, and then we increase it to 0.25. So replacing 3 tools, a milling cutter, a center drill, a drill. So more time saving, 3 minutes per part. And the HPC effect, tool and tool changing is saved, so the downtime of the machine is saved. And we have another three free pocket seats also in our tool magazine. This die and mold application. When you look to the component, my first idea when I saw this component will be, let's drill the hole first and then we do the milling operation. This is exactly what the owner of this component did. But he was facing the problem that these holes were filled up by the swarf of the milling process. And the milling cutter, it was a 4 milling cutter with expensive inserts, is cutting always into the swarfs. And this was damaging and was decreasing the tool life of the milling cutter. So then he decided to change the operation. First, do the milling, and then we go for drilling. And to convince the customer, we did such a component on his machine. It's very important to get exactly his conditions, not to do it on our machine, maybe with the HSK 100, very strong and rigid conditions. Maybe this was an ISO 40 machine, ISO 40 taper machine, or a HSK 63. So then it looks completely different. You see what we have done here? Drill between existing holes. There's such an operation here. 2 holes were existing, and we drill another hole somewhere here in the middle. Drilling on edge part with a 15 millimeter, 10 millimeter, 5 millimeter overlapping. This was this situation here in this area. And also here you can find only half pipe bores. And it's 5 times D. Completely interrupted cut. So now tool life gain in milling by drilling last, so by doing drilling the second operation. This nice component, this was a cylinder bush, I think was a compressor, from a compressor. It's 42 chrome molybdenum steel. They called it a shreddering machine, but I think it was a compressor. So what they do first, we have to do a hole dia 20H9. We do this roughing normally with a circular milling operation, dia 16 from 2 sides. This is very logic for such a bore, such a hole, which is never ever in the solid, which is only doing interrupted cut. So the total machining time was about 100 minutes for these 5 components. So when we changed this drill, or this from milling into drilling, only from one side, with a dia 19.5, 120 meters, 0.04 feet. So it's not so much feet, but it makes the drill a stable process. And the HPC effect, yeah, we save 3 tools, and we are reducing the machining time to nearly 90%. So 100 minutes before, we do now this in roughly 10 minutes, all the holes. Another option to improve the process will be roughing and finishing in one tool in one shot. We call this tool a Bretzicom tool. So how is this possible? I can do roughing or I can do finishing. If I do roughing, I have rough inserts, I have a very stable insert seat, I have 4, 5, 6 cutting edges, and if I do finishing, maybe by a boring tool, I have 1 cutting edge, what I can set, or I can go for a reaming operation, maybe single blade reaming or multi-blade reaming. But this tool is combining both process into one tool. Look at this. Normally, we go for a twin cutter for open a bore in a cast iron component. Then we go for finishing with a reamer. But both tools together are a tool like this, roughing and finishing in one shot. So how do we do this? In first, H7 will be difficult, but H8 in cast iron and nodular cast iron is today the practice. When you look to the tolerance fields, H7, H6 and better, you should go for a typical reaming tool. But therefore you need the pre-machine operation. You need a boring tool first or a drilling operation first. So we have stock allowance of maybe 0.1 to 0.5 millimeter what we remove. But if you go for such a tool, you can achieve H8, H9 glass holes, and the stock could be 4, 5 millimeter easily. So it's a typical cast contour, what you're doing directly, a seat, a bearing seat, into your cast contour of your component. A very typical component, and I don't tell you a secret, this tool comes from such a component. It's a brake caliper, and in a brake caliper you can find a bore, which is called the piston hole, the piston bore, and this is normally a H8 glass bore, and in this component you can find 2 millimeter, 3 millimeter, 4, maybe on the bottom, up to 5 millimeter stock, what we have to remove. And to save time, because this is a really mass production, yeah, we create this tool where we can do the roughing and the finishing in one shot. To do this, the 4 cutting edges are all adjustable. That's point 1. With a very sensitive wedge adjustment mechanism, and the corner on the outer side where we create the diameter is very similar to a reaming tool. We have a circular land on this insert, but a circular land which is not ground according to diameter. So we have a big range of diameter where we can use the same standard insert, so it doesn't have to match exactly the whole diameter. Here stock 3.5 millimeter IT8 class, RZ 10, 2 life, 55 meters. I don't know how many, and per set it's more than 200 meters. So it's thousands of components what we are doing with one set of inserts. A last tool I like to introduce to you, you know, reamer rings like this. These reamer rings are normally brace type. So the cutting edge is fixed by a bracing operation, and after bracing we do the finishing. We have such reamer rings still in our program. We do the finishing according your diameter, what is required by you, into a tolerance of, let's say, H7, H6. The whole ring is adjustable by expanding. In the center you can find a taper element. If you press the taper in, the whole ring will expand, and you can set the tool in the tolerance field. So the product description and the features are modular tool system with multi-blade. It's not just a single point reaming, it's multi-blade reaming. The diameter range up to 110 millimeter in standard and up to 300 millimeter in a special tool. So expandable or adjustable in a range of 30-40 microns, so 3 to 400 still. That means after your size drop down and you reach the lower side of the tolerance, you can increase it 2-3 times to remain in the H7 tolerance. Each of these inserts, what we are mounting here, have 2 cutting edges. So this ring has two lives, completely two lives. Yeah, standard cutting material and 6, 8, 10, 12 numbers in the reamer ring. So what will be new now? What will be the benefit? The basic holder is from the existing tool program, so we don't need another holder system. We just take the old-fashioned style off and put the new holder or the new reamer ring on. A better tool life for the whole body. You can expect when we do a refurbishing, a retipping of a brace type holder, it's a heat treatment what we have to do. And this could be done maybe 2-3 times, then the ring itself reaches end of the tool life. And with this reamer ring, it doesn't matter. I don't know how many inserts what we can mount. If you don't have a crash, I think it's hundreds of inserts what you can mount on this holder. Yeah, less numbers of tools are needed because this holder is more or less available and you can reduce minimum to 50% the whole numbers of tools. So at least it's saving costs and for the reamer ring itself, and your costs are only the costs to run the tool for these inserts. So what will be the product? When we supply such a reamer ring, it's a question of the logistic. It will not be possible. We should be open also in an exhibition. It will not be possible to sell you one ring and to sell all the time the new inserts. It's not possible to achieve a H7 glass tolerance. We need the ring to grind the inserts. So if you have to turn round, you have used your second cutting edge, you have to send the ring back, and we are mounting new inserts on the ring, and then we are grinding the inserts and we do the coating in a assembled condition. Just to show you the principle, how this is working. Here you can see the basic holder, that expandable reamer ring with the indexable inserts, and this taper screw. So we have just working our tool life once. Then you are turning around the inserts. The inserts are mentioned with a number, and the insert seat is mentioned with a number, so you know exactly which insert belongs into which seat. And then send the ring back, and we do not retipping, but we equip the ring now with new indexable inserts. Yeah, the user strategy and the cost saving looks roughly like this. Normally, a brace type ring plus 1, 2, 3, 3 times retipping will be possible. Maybe for another 3 times we need another ring, for another 4 times we need another ring, and another 3 times, and another ring, another 1 time for retipping. Then we have 10 tool lives. Yeah, with a ring with indexable insert, we have to have 1 ring, and we have 4 sets of inserts. And this makes a cost saving of more than 40%, which is reducing tool costs and is reducing also the logistic costs what you have automatically in your company. I think I'm again right in time. And I'd like to finish my presentation here, and I thanks really a lot for your attention.